Welcome to this webinar. We're going to wait a few minutes for welcome to this webinar. We're going to wait a few minutes for a few more participants to arrive. We'll start in 5 minutes. Still just a few more minutes to leave some time for the latecomers, and we'll start in 3 minutes now. So welcome again for this new webinar about Zetamix and our technology for ceramic and metal 3D printing. We'll start now. Before we really get into the topic, I just like you to remind you that obviously this is an interactive event. So if you have any questions during the presentation or afterwards, you should really feel free to ask them. This is really the purpose of these webinars. So if you want to ask questions, there's a Q&A section, which is on the bottom of your screen, which will be quite convenient for that. So let's start. As an introduction, why do we make a webinar about really how the technology works? We usually like to focus on the applications, on what our customer do with that, what it brings in terms of value. But we had a lot of inquiries for that because a few customers just can't believe this is actually working. They can't believe that it's possible to print ceramic and metal parts on any FDM printer. So we felt it was necessary to, well, really show you how that works. And again, the idea is for you to be able to ask any question you may have about how does it actually works. Of course, we will do some more webinars about applications, which is for us really the more important part of this, about the materials, about all of these other aspects of the technology. But today we really wanted to focus on how does it actually work? How does the system make parts? A short introduction about the company for starters. For those who have followed us in the previous webinars, you already know that, of course. But still, a short reminder that who are we at Nanui? Nanui, we are a raw material producer. That's really the one thing you should remember is our job is to provide raw materials for the industry. And not only for 3D printing in general, we provide raw materials for ceramics and also a bit for metal in forms of powders or any feedstocks required by our customer. We have a strong focus on innovation. The company is still a relatively young company. We're 12 years old, and we're still very much focused on developing new materials usually with customers, and at the moment developing new materials for 3D printing. What does our customer do with these materials? Well, they make mainly ceramics, a bit of metal, but mainly ceramic parts. And to make ceramic parts, it's always the same principle. You have a two-step process, a shaping process, and then sintering, which is a high temperature treatment. And this is the same whatever the process used by our customer. It can be pressing, casting, injection molding, or 3D printing. This still remains a two-step process. The first step is here to shape a ceramic body, what we will call a green part, and then sintering will give you the actual properties of the material, which means that for ceramic manufacturers, all these specifics about what happens during sintering is something which is very well accepted and very normal. It may not be the case for you because you are not maybe very well familiar with ceramics, but this is completely normal for a ceramic manufacturer. And when we do 3D printing, we are just replacing this shaping process, which could be pressing, injection molding, by another technique, but the principle stays the same. What kind of applications do we find these ceramics in? Well, any kind of high-tech applications where you need really very performing materials, semiconductors, aerospace, medical, wear parts, fluid handling, all of these applications, we need ceramics because they give heat resistance, wear resistance, electrical resistance, and a few other of these applications. We do have an application for aesthetical parts also, mainly in jewelry and watchmaking. Again, this is in general for all of our materials, whether they are printed or shaped in another way. That doesn't really change the applications we may have. So let's focus now on what we bring to 3D printing. We started working on 3D printing material in 2018. So that means 10 years after funding the company, which really means that it's not it's not our core business. Initially, our core business is, again, in providing raw materials for industrial process. And we decided to go for 3D printing because that obviously felt for us as a very promising market and market that will grow. But we decided to go in that market in a different way from what was already existing for ceramics. We wanted to develop a technology that would make ceramic AM affordable and easy to use, which is not really the case with other technologies. And this is really where we put our focus, which is why we chose to develop a FDM technology first. So basically, what do we do at Nanoe? At Nanoe, we're going to make materials. That's what we do. We provide raw materials. So in this case, we're going to provide mixes of thermoplastic and powder, what we call feedstocks, which can be for ceramics or metal. But anyway, it's always the same principle. We mix a few different thermoplastic binders with a lot of ceramic or metal powder to get to very high loadings of powders. These feedstock, they can be used for injection molding, but they can also be extruded into highly loaded filaments. And that makes filaments available in alumina, zirconia, and also in stainless steel. Just an explanation of that. So the compounding phase is where we will mix the powder and the binder, and extrusion is what will give us the filament. So that's really what we are good at. So we're not a machine manufacturer. We do offer a few systems, but we don't manufacture them. We're not a part provider. This is the job of our customer. What we are good at is at providing the raw materials. So powders, compounds, and filaments. And then how do you use these filaments? It's something which has started to be quite well known, mainly a three-part process, which are the three parts in the middle: printing, debinding, and sintering. So when you print the part, you actually print a mix of thermoplastic binders and powder. And then in steps 3 and 4, you're going to eliminate the binder and make a very high temperature heat treatment to densify the part, to give it its strength. Obviously, before that, you need to prepare the file for printing, and after that, you can have some post-processing. We'll go into the details of all of this process, but it's good to see the full picture before starting to get really in the details. Let's start with file preparation. Here we're really going to do it in a demonstrative way. So I'm going to get out of my presentation and open the slicer so that you can see. But basically, what are we going to do when we prepare a file? Well, we use softwares that will transform a 3D file into a set of instructions for the printer. This includes, of course, loading the part in a slicer, positioning, scaling, and then really giving the instruction so that the slicer will decide exactly the tool path of the extruder. And we'll go in details. I will show you in details mainly the 10 main parameters that are really important in a slicer. I'm not going to go into the details of all parameters because you actually have hundreds of parameters available in a slicer. But really, with these 10 key parameters, you already manage to make good prints. So let's get out of this presentation and start to have a look at what a slicer is. So this is a very well-known slicer. It's an open source slicer which goes with the printers of the brand Ray 3D, but which can also be used with different printers. And here we already have a part. This is just a small ring, quite simple, which is one of our very usual standard part that we print quite all of the time. It is loaded in the space. Here you can see materialized the space of the printer, the size of the space, which should be 30 by 30 by 30. Now, if I go to the part, the first thing I would do is load it on the plate. It's already been done. Scale it, because as I mentioned very quickly, during sintering, you're going to have a shrinkage. And to compensate it, we're going to scale the part before printing, which is very easy to do. You select the part, you click on scale, and you will enter here some data that we provide our customer about the oversize factor you need to apply. Here we're printing with black zirconia, so it's 126.9% that you need to apply so that you have the right dimension at the end. So another part is the right size. It's a pretty straightforward part, quite simple to print. So we're going to go directly to slicing, to preparing the file. And that's quite simple. You click on Start Slicing. You select a profile, the profile you've predefined for the material, and you just click on Slice. And that's it. The material, the part is ready to be printed. We can have a look here. This is an example of the tool path that will be created for this part. Now, this is really if you want to be quick, so you just use the preset parameters. Still, I told you I would show you a bit of the important parameters, so we're going to go backward a bit. We're going to do that again, but we're going to have a look at the slicing parameters. Again, I click on Slice, and instead of directly clicking on Slice, we're going to go a bit deeper into the parameters of black zirconia. Just by double-clicking, you have an access to the advanced settings. You can see here that we will have literally hundreds of parameters accessible. It's a bit too much. It's a bit overwhelming, which is why we're going to start with the more important one. The other ones, honestly, for starters, you don't need to get into too much details. So the first very, very important parameter, of course, is layer height, which is the size of the layers you're going to do. The typical size we usually print is 100 micron, 0.1 millimeter. This will give you a good compromise between speed and quality of the part. Sometimes if you have a very big part, you may want to increase that. You can also decrease it a bit, but the limit is close to, I would say, 50 to 70 micron. So we are relatively close to the limit. Usually 100 micron, again, is a good compromise, so 0.1 millimeter. Second really, really important parameter is the shell. You may not have seen, and I'll show you again later on, but the part is divided in a slicer between the outside region of the part, which is called the shell, and the inside, which is going to be called the infill. Here we are going to define the thickness of the shell, and we define it in numbers of nozzle size, basically. So the nozzle is 0.4. So if we put 2 shells, the total shell is going to be 0.8 millimeter. This seems like a reasonable figure. We can leave it here. We could want to do it a bit thicker and maybe put 3 shells. Why not? That's for the first tab. That's really the 2 most important parameters. I'm not going to go too much in detail, so we're going to go directly to the second tab. Here you have 2 really very important parameters: extrusion width and retraction. Extrusion width is the exact pass size. So your nozzle at the moment, it's 0.4 millimeter. It could be another size. You could print with bigger or with lower, but for the moment we have a nozzle of that size. But you can decide to print a pass that is going to be slightly bigger or slightly lower. Usually with ceramic and metal filaments, we choose to extrude a little bit more than the size of the nozzle to increase adhesion. The second really important one is retraction. What's the interest? What is retraction, and what's the interest of retraction? Retraction is an added comment you will put in a slicer, which will force the filament to go backwards. Sorry. Will force the filament to go backwards when it's not supposed to extrude. Why do we do that? It is because if you don't do that, you will actually have a bit of filament which will keep oozing even if you're not pushing the filament, just because it's melted. And so you will lose a bit in precision. You'll have a few small strings here and there on the part, and this is something we want to avoid. So we usually put retraction, but this is something quite critical with ceramic and metal filaments, because ceramic and metal filaments are quite brittle, and you want to avoid being too hard with them. So we usually put retraction, but we will decrease the speed of retraction. That's all. We'll put a relatively slow speed. That's it for this tab. So here are again two important parameters: extrusion width and retraction. We go to the third tab, infill, where we're just going to decide the density of the inside of the part. One of the big interests of FDM printing is that you don't need to print a fully dense part. You can make the inside completely hollow, or you can fill it with any kind of structure and with any kind of density. So here we decide to put 50%, which seems again a good figure, of infill, and we can choose to have honeycombs, grids, gyroid, whatever. We'll start with honeycomb, which is a very simple, very well-known parameter. Fourth tab is there's one which is important here, which is the bottom and top solid fill layer. Basically, we have defined the shell, which is the wall on the outside of the part. We have defined what we put inside, but we haven't decided what we put on top and on bottom. And we need to decide, do we want the top and bottom to be dense, or do we want it to be just like the infill? If we want it to be dense, we will add a few solid fill layers, and we decide the numbers of layers. 5 is usually a good number, so we're just going to keep it here, 5 and 5. Sometimes we decide to have solid layers on top and not on bottom, or the reverse. That's also something completely open. Then there's supports. We'll talk about supports later on. So for the moment, I'm just going to remove the supports. That's a bit more simple. Platform adhesions, which will be helpers if you have problems of adhesion, but usually it's not so much of a problem for ceramic and metal. Cooling, this is really something critical. The way the technology works is that you actually melt the plastic by pushing it through a heated nozzle. But once it's melted and deposited, you want it to cool down as fast as possible. And this is ensured by small ventilators that will blow fresh air just outside of the nozzle. And here you can decide how strong you blow air. Basically, it's pretty simple. With ceramic and metal, we usually just cool as much as possible. Because of the density of the material, we really need to evacuate heat, and that's usually 100%. Temperature is, of course, important. The extrusion temperature is really critical. One of the interesting things is with our materials, we usually don't need very high extrusion temperature. We're usually below 200 degrees C, sometimes 220, never more, which means it's compatible with most printers. All of the printers can go up to 220. You don't really need a heated chamber. You don't actually need a heated plate. So that makes it really compatible with most printers on the market. And the last one, obviously, is printing speed. This is really of importance. If you try to print really too fast, you may have a few problems of filament breakage, nozzle clogging, or just imprecision in the part. And of course, if you go too slow, you're going to end up with a part that takes ages to be printed. So you need to find the right balance. Usually, sometimes something in the range of 20 to 30 millimeter per second is the correct value for our materials. So that's it. Here we've really seen the main parameters. Again, I'm not going to go in details on all of these parameters. That would take too much time. So we can save. And again, we can click on slice. And by clicking on preview, you will see the part as it is prepared for the slicer. Again, we can check, we can see the layers in red. And here you can go down and see how it looks inside. You can see quite well what is The red is what we call the outer shell, the green is the inner shell, and then you can see a little bit of infill. There's not so much because the part is not very thick, so you don't see the infill yet. We'll show you a second part afterwards so you can see that. Once we're happy with the printing parameters, we just export the file to any USB stick, put it in the printer, and we're ready to go. That's it for the simple parameters. I'm going to go back to my presentation quickly to talk to you about the next important thing, which is supports. Here we had a part which was relatively simple, so there was no need for supports. But in some cases, you'll find out you have some parts that you cannot print without putting any supports. And then you'll need to think about what kind of support strategy do we put in place. Do we just print support with the same material or with a second material? Do we put supports everywhere or only on the plate? What kind of size do we put for the supports? And do we generate those supports manually or automatic? Here again, I'm going to show this directly. So we're going to change the part because this one is a bit too simple for supports. We're going to upload a new part, which is here, which is a demo part we use quite often. Obviously here it's not very well oriented. We're going to put it on the flat surface here, but you will find out that this does not solve every problems. Here we go. So here it's flat on the plate. You can see that most of the part will print well, but you do have a few difficult places. Typically, this angle here is impossible to print as it is. This one also seems really critical. The other ones should be okay. There's the question of these holes inside. Are they going to be printed well or not? This is something that can be tried. It depends on the size of the hole. Anyway, there is some questions about supports. So we need to generate supports. We can do it here directly before slicing. There's a tab which is called support. And we can ask him to create auto support. I need to select the part to do that, of course. And here you'll see there is some supports here in the holes. Here we don't see them very well, but there's also on the bottom of the part here 2 small cavities where you have supports. You could decide to say, okay, this looks good, but I think that for the small hole I don't need it. So manually I'm going to remove it. Here we go. Just by clicking on removing and on the one support that I don't want to have. This one may be necessary, so I leave it. So you have the possibility to adapt it a bit by yourself. You can also decide not to do it here, but to do it at another place. So we can remove all of the supports and say we're going to give the instruction to the slicer, and the slicer is going to do the job. So again, we go in the parameters, the printing parameters, and we go to the support tab. In this case, we're going to ask the slicer to define where we need support or not. We can ask him to put supports only on the platform or everywhere. Let's say we put it everywhere. We can decide which extruder it's going to be. Is it the same material or a second material? We can decide the type of support. Is it just a normal support or a pillar, just like what we saw previously? Is it lines or grids or whatever? And what's going to be really important is we're going to define what we call a max overhang angle, which means any angles of 45 or less, we are not going to put any supports. If you have more than 45 degrees of angle, we will add some support. If you do this and you just save and slice, we are going to see those supports installed on the here you are. You can see in blue the supports here, and there, and there, and obviously in the holes again. If we go down, we'll see all of them. We also see here a bit better than previously the infill. You can see the yellow, which is the infill in the part. And here you go, you can see really well the infill, which is honeycombs here, and the last support, which are in the small cavities here and there. So again, you have a complete control over this. You can decide to have it only on the plate. You can have it on the plate and on the part. You can decide the kind of support you want. And all of this is generated automatically, which makes it really very convenient. Again, once we are happy with the file, we can export it to any USB stick, put it in the printer and print. That's it for supports. So now we have prepared our file with supports. We print the first part. We're really happy. It looks great. But we may find out a few problems, and we wanted to point out a few troubleshootings that you may have to do. The first thing is you may have to optimize a bit your file to avoid having big defects. These are typical defects we see when the slicer parameters are not right. Here you have an example where you really see each pass of the nozzle and with relatively big porosities, which are triangular shapes, here, here, and here. Here on that side and on that side, you see the same effect, but just on the side of the part. Here it was in the full part, and here it's just on the outside of the part. So it's two typical defects we're going to have. The case in the middle is just that we are what we call under extruding. We're not bringing enough material in general. So we need to increase what we call the flow rate, the amount of material we're going to put for 1 cubic centimeter or whatever. The amount of material we extrude when we move of 1 centimeter. You define it as you want, but the flow rate is a bit too small. It's usually defined in percentage. The settings are usually 95 to 100%. And sometimes we need to increase that if we feel that we have a density which is a bit too low. This kind of defect, which is just on the outside, is a bit different. It's actually because there's a bad junction between the shell and the infill. And again, there's one parameter for that, which is called infill overlap, which will tell you how much the infill is going to overlap on the shell. And it needs to overlap a bit, typically 30 to 50%, to avoid that kind of defects. So really, there's some fine-tuning here. Of course, we give preset parameters to our customer, but it may depend a little bit on the part you are printing. Another typical problem you will have in the next process, you're going to have a part which looks really great after printing, but during debinding or sintering, it cracks. How do you avoid that? How do you avoid cracks during debinding and sintering? There are a few things. The first one is we need to avoid having high thickness. If you have thickness of more than 5 millimeters, you're starting to be in a, let's say, dangerous region, and we know that more than 10 millimeters of really dense material, of fully dense material, is impossible. We can't make it. So how do we go around that problem? Well, if we put an infill in the part, so that means the part is not fully dense. Inside, we're going to put a gyroid or any kind of grid or whatever infill you want, but we will avoid having a fully dense part. If possible, this infill, we're going to try to make it accessible for the debinding. So if it can be open on one of the side of the part, it's even better. We also need to avoid any sharp angles because this is usually where any cracks will initiate, and we need to avoid brutal changes in thickness. So that's also that's more actually in the CAD, the design of the part than in the file preparation. That's it. So once we've done all of this, we're ready to print. We have our file on a USB stick. We go to the printer, we put it inside, and we are going to print. Of course, before printing, we have a few things to prepare. We need to check the zero level of Z. We need to load the filament, and then we can launch the print. Here's a short video that shows you how to do all of these steps. Yeah. Here we go. So we see our operator loading the filament. We have it's a print. The printer we're using is a printer from Race 3D, which is a very well-known brand. We do modify it a little bit for those who are familiar with the printer by adding a specific spool holder, so that the spool is really on top of the extruder. You will notice that actually the operator is quite careful during the loading because the filament is quite brittle. And this is why this is also put it on an adapted spool holder, because of the brittleness of the filament. So loading is quite simple. We're just going to push the filament in the gears. Here we just open the gears so that you can see what happens. Usually it's closed. During the loading, the gears will just push filament, and we insert it, and it's going to be pushed to the nozzle. You can see the filament coming in, and I guess at some point it's going to close the lid. Usually we don't need to do that. We just did it to show you how the gears rotate. So the one nice thing about this is the printers, FDM printers, it's very simple. You just have a small motor pushing the filament with two gears through a heated nozzle. There's really nothing more simple. So here again, you can see we are preheating the nozzle, and then we will push the filament, and we are going to wait to see a bit of material coming out of the nozzle. We usually wait a bit to make sure that the filament is really primed. There's no more air, any bubbles, anything inside the nozzle, and it's ready to print. Of course, we need to check the Z level, so that's done pretty simply by what we call homing the extruder. We're just going to tell the printer to go to 0, and we are going to check that there's still a small gap, a very small gap between the nozzle and the plate. That's what we aim at. We want the distance at 0, the distance between the plate and the nozzle should be quite small, something like 100 micron, but not 0. We have a calibrated tool to do that. If it's not good, we can set it by turning a little knob on the side, repeating and checking until we have the right the right settings in 0. Okay, I guess this time we are close to it. Well, I'm still homing. This is really critical. If you have a bad calibration of the 0, you're probably going to ruin your part and your print. So we really advise our customer to do that quite often. It saves a lot of time to calibrate properly the Z level. In the same way that it also saves a lot of time to clean the printer quite often after printing. This is really critical. I guess we're ready. And then we go to printing, and then afterwards, plate removal, support removal, everything. You'll see that in the next video. This one is pretty simple. So we have the first part we show at the beginning, and we just click on print. And here we go. So we have a short time lapse, which will show how this is printed. Maybe you can see it, but we are printing with an infill, which means that the part is not fully dense. We can see that a bit if you have a trained eye, and you'll see the parts growing progressively. A part of that size takes typically, I don't know, something like 40 minutes to print for a ring, and that's it. So what are the main problems you may have during printing? The two really main problems are nozzle clogging and some filament jamming in the extruder. Nozzle clogging can happen, but usually, really, if the printing parameters are good, if you're careful about the first layer being laid correctly, it's pretty rare. And when it happens, well, you just have to unclog. There's nothing else to do. Using a small needle or whatever, you need to unclog the nozzle. Filament jamming is something that can happen for several reasons, but usually it's linked more to printing parameters not being the right ones. We're printing too fast, or we're not printing at the right temperature, or something of that kind. Again, the filaments are quite brittle, so everything that's out of line in terms of printing parameters may end up with that kind of problems. Once we have a part which has been printed, we've removed it from the plate. I forgot to precise that the plate is flexible, which makes it very easy to remove the part from the plate. Once we have a part, we're going to do the rest of the post-processing, which is debinding and then sintering. So debinding is done in a two-step process. We first make what we call a chemical debinding. We dip the part in solvent, and then we do a thermal decomposition to remove the rest of the binder. So the first step is just dipping the part in acetone, which will remove part of the binder. As you can see in the picture, the binder composition we have are usually at least with two different components, sometimes a bit more. And one of them is what we call a soluble binder. It's going to be removed by the solvent, and the other one is what we call the backbone, and it really needs to be burnt out. We are working for metal especially, but it may come one day for ceramics also. We are working on filament that doesn't need any solvent extraction. That could be done completely thermally, but that's a bit more complex to achieve. So the binding is done in heated acetone baths, and one of the really important things we say to our customers is the first thing is you need to respect the guidelines. In the guidelines, we give you times for debinding depending on the thickness of the part. And the second thing is you really need to check that you have the correct mass loss after debinding, which means you basically weight the part before and after debinding. So here you can see how it's done. It's pretty simple. We heat up the bath, and we put the part in a small basket. You open the acetone bath and you just put the part inside. That's really very, very straightforward. And a few hours before, a few hours later, you have, sorry, a small surprise from my marketing team. A few hours later, you have a nice debinded part, which you just leave to dry for a few minutes. Acetone dries quite quickly. Maximum 1 hour after that, you can usually put it in the furnace. Here, interestingly, you can see the part before and after debinding. There's already a very small shrinkage between the two and the change in color, which is really completely normal. But that's usually interesting to see that. Then after we've done that, we're going to go to sintering. What is sintering exactly? Sintering is the kind of densification which happens while the material stays solid. We're not melting the material, of course, or we would lose the shape. We're just densifying it at very high temperature. We go to densities up to 99% for ceramics, usually more 90% for metal, which means a shrinkage. If you start with a part which has a density usually between 50 and 60% once you have removed the binder, and you want to go to 90 to 99%, there's no miracle. The porosities, they go to need somewhere, or the material needs to go somewhere, and that means you need to have a shrinkage. And usually it's a linear shrinkage of 15 to 20%, depending on the material. Importantly, it's a relatively homogeneous shrinkage in the three directions. So then there's sintering. Sintering is done in a tube or a chamber furnace with sintering temperatures, which usually range between 14 and 1600 degrees C. We sinter in air for ceramics, and there's a big difference here. When we want to do metal, when we don't want to do steel, we need to have a neutral gas. Usually it's argon plus hydrogen. For stainless, sometimes you actually need pure hydrogen, which is quite a problem, which is not something we can do with our furnaces. You need a special furnace. And we are also launching very soon a new steel, a tool steel, which can be sintered under nitrogen in its case. But in any case, you cannot sinter a metal under air because you would oxidize the metal, of course. So here's a quick demo of sintering, how it's programmed, and how we put the parts. So here is the programming. The programming has already been done, so we just check it. We just don't need to modify it actually. And then we just put the parts on plates, and we insert the plates in the tube furnace. Here it's a tube furnace. The big interest of tube furnaces is you can use them both for ceramic and metal. It's very easy to put the tube furnace under neutral gas, which is a bit more complex for chamber furnace. So when a customer wants to do both material, we usually advise to use a tube furnace, and if he wants to do only one material, he can use a normal furnace. Here we're showing the setup that we would use for metal sintering. So we would close completely the furnace and have a flow of gas gone through the material. You can see here it's quite simple. You just have to plug the gas flow on it. And the sintering takes between 24 and 48 hours, depending on the thickness of the part. Usually it's more in the range of 48 hours because of the thermal debinding more than the sintering itself. I didn't precise it, but you do have here, this is what we call a heat shield. It's a porous ceramic that will keep the heat inside the furnace, and then you can get the part out. You are. And here is the part after sintering. You can see here the main part of the shrinkage happens during sintering, of course. Once you've sintered the part, especially if you're making a ring, you may want to finish it, to have a nice surface finish. This can be done manually. There's a lot of manual methods for polishing. You can do it with a few rotating tools. And one of the most effective way to do that is tumbling. You basically put the parts in a tumble with some polishing media, and you just let it turn for quite a long time, and this will give you some nice polished parts afterwards. Here is again the same parts after tumbling. Well, that's it. Once you've done all of these steps, you have a ceramic or a metal part. What are the key advantages of this technology? Well, the first one, really the most important one, is that it's quite easy to use. You saw the steps compared to any other ceramic or metal AM technologies. This is really the most simple and the most affordable way to print ceramic and metal. We train people, usually when we train a customer, it takes 1 day maximum before you can print parts. And it can be used again by any technician. You don't need to have a very high-end setup. You don't need to have highly trained engineers. It can really be used by anyone who had a proper training. And another good point is that there's very little health and environment issues. There's no volatile powders, there's no toxic materials. It's much more simple than when you deal with free-flowing powders. The second big point is it's a low-cost investment. The printer plus the furnace plus the debinding kit, all of these starts at 10K, and there is no equivalent on the market. There's nothing that can compete with that. Of course, it won't do everything. You may need other technologies for other parts, but for most of the parts you may have in mind, this is really more than enough, and it will really help customers getting started in additive manufacturing. It's a quite versatile technology. To my knowledge, it's quite one of the only one where you can actually print plastic, metal, and ceramic on the same printer. We have in the range at the moment alumina, zirconia, stainless steel. As I told you, we are launching a tool steel, and we have in development silicon carbide, tungsten carbide, silicon nitride. A lot of material can be printed in that way. The last thing is, usually when we talk about FDM, people tells us, well, it's not precise enough. And sometimes it's true, of course. But still, the accuracy is really much better than what customers actually believe. We get to precision of plus minus 0.1 millimeter on parts that are typically 100 millimeter before sintering, and which will go down to 80 millimeter. There's also that possibility to print very small internal details. You can print closed porosities, you can print internal channels, hollow structures. There's a lot of things that you can do with this technology that you could not do with another one. That's it. Thanks a lot for your attention. And now I'm going to go to the questions. I don't know if there's a lot of them. Of course, you're really very welcome to ask your questions again in the Q&A section. I'm just going to stop sharing my screen and go to the questions. The first thing is not a question. Thank you, Reda, for your nice appreciation of our efforts. We do try to make the technology understandable, and that's really what we wanted to do here. What is the cost for zirconia Zetamix feedstock? So if you talk about the filaments, the costs are usually between 500 and 600 euro per kilo. Zirconia is 600. We do have quite a few questions about cost. When people compare the cost of the filament to the cost of the zirconia powder or the cost of the feedstock for injection molding, there's difference in prices. To make it simple, the filament costs probably twice the price of feedstock for injection molding, and again a bit more compared to the powder itself. But really, when we count down to the price of the printed part, the price of the final part, we usually find out that between the fact that by making it by additive manufacturing, we remove all of the tooling cost, and also we make a part that is lighter, so there's less material in it. We usually find out that the end cost calculation for the part is really very positive. So by which machine and method do you mix and extrude the compound to make filaments? Well, this is a bit of our secret sauce, you know. I'm not sure we want to communicate a lot on this. We've worked a lot both on the feedstock formulations, and we have also worked a lot on the process itself. Extruding a filament which has more than 50 volume percent, which means more than 80, sometimes 90% in mass of powder, is really not an easy feat. It's something quite difficult. So we've worked both on the material side, but also a bit on the machine. So I'm afraid I can't answer to that question. So should the printer closed printing area or open is also okay? Well, we've tried our filaments with a lot of different printing technologies, a lot of different printers. Some of them were open and it works quite well. To give an example, we've printed excellent parts with a Prusa printer. Prusa is really the most simple desktop printer you can imagine. It costs less than 1,000 euro, and the filament works well with these printers. We still feel that it would be safer to have a closed area, because in that way you are sure that you don't have any interference. I don't know if it's cold outside or if there's too much humidity. You may wonder, well, my part failed. Why is that the case? If you have a closed area, you're sure that the outside doesn't matter too much. What is the lifetime of the nozzle? Knowing that ceramic is abrasive, you're right. Ceramics are very abrasive. In the past, we've considered going to very wear-resistant nozzles. We've looked at ruby nozzles or hard metal nozzles. And in the end, we went back to using brass nozzles, which are really not wear resistant. What we found out is that, yes, they were done, but not that fast. And that we just decide to replace them before it's a problem. So typically, we're going to replace the nozzle every 1 or maximum 2 spools. But when you know the cost of a nozzle, it's really nothing, so it becomes a consumable. And we felt we had better results with brass nozzle because brass has a better heat conductivity. Is it possible to pour molten bronze inside a ceramic part? I want to do a 2-part component and wonder if this will work. That's an interesting question. We do have a few customers who are looking into using a system to print molds to make casting. But in that case, the mold is supposed to be eliminated afterwards. So that's not exactly what you want to do. In your case, I would say that there is a possibility. You need to be very careful about thermal shock, which is going to be a problem. That means if you just pour molten bronze in a cold ceramic part, you will probably crack the part. If you're careful about that, if the heat cycle is reasonable, might work. I must say I've never tried it, but this might work. Is Z shrinkage the same as in X and Y? It's a good question. Hello, you're right. Most of the technologies we've seen on the market, X, Y, and Z, are different. For ceramics, we haven't seen a very significant difference. Sometimes there's a bit of difference if you do a really long part, very high part. And there's a very little bit more shrinkage in Z, but it's very hard to discern. For metal, it's a bit more pronounced. And yes, we have a different Z shrinkage for metal compared to X and Y. I cannot tell you why, it's just the way it is. For ceramics, there's not much of this and a bit more for metal. So what are the size limitations with your current 3D printing machine? And could you please share the example you made for aerospace industry? So regarding the size limitation, the printer itself is quite big. We can make 30 per 30 per 30 centimeters. There's another version of the same printer which even has a Z of 60 centimeters. So you're starting to make relatively big parts. We're more limited by first the sintering furnace. The furnace we offer are relatively small. Of course, the customer can decide to buy another furnace. I mean, we are on an open system, so you don't have to buy the furnace from us, but you would need a bigger furnace. And there's a second thing, which is that this makes really let's say the sintering more difficult to control, and especially the shrinkage. You'll start having part with a bit of distortion. You'll start having a few difficulties. It's doable, but it requires a bit more know-how. It's a bit more difficult. In terms of parts made for aerospace, well, we actually did another webinar on this. I'm afraid I'm not going to do it in full. I can show you maybe just a few pictures from that webinar. It was actually a webinar we shared with one of our customers, which is always great. We like to put forward what are the actual applications for these. Maybe I can just share a few pictures of what our customers did. We saw a few applications. One of them was what we call, I'm going to share my screen if you wait for a minute. Here's an example of a part that was made for aerospace. It's a very high temperature probe made to measure speed of flow. So it was a relatively big part for us. We're not used to make such big parts. But again, it was made by a customer, which is called Avignon Ceramic. And this part is supposed to go up to 1600 degrees C, and the internal channels that you can see a bit everywhere on the parts are made to measure the speed of the flow of air, basically. It's called a pitot probe. And here you have another example where we made filters for foundry for aerospace applications again. That's a few of the examples we had in that field. The example of the probe, and I think I could also show another example of such probes, if I can find it. Right, it's going to be in another webinar. The interesting thing with that kind of part is that it's actually very, very straightforward to print. But if you wanted to do that by a traditional process, it's completely impossible. Here you have another example of the same kind of parts that were done again by a customer, Avignon Ceramic. The principle is again what we call a flow sensor or a pitot probe again. The principle is that you have a channel here that will measure pressure, what we call the dynamic pressure, and on the side you have other channels that will measure the static pressure. And by making the difference between the pressure in those two channels, you can deduce the speed of the flow of gas. And again, making that part with these internal channels, it's a very simple part. It's not very big. It's very easy to print. But making it in any other process would be completely impossible. That's what was interesting here. Here are a few examples of what we did in the aerospace sector. What is the shelf life of the filament? That's an excellent question. Would say the filaments are delivered in vacuum sealed bags. As long as you don't break the vacuum sealed bag, it can hold up to 1 year, no problem. Once you have opened it, it's better to use it, let's say, in the space of 1 month, maximum 2, because after that, the filament will still be usable, but it's going to be a bit more brittle. Is ultrasonic bath required for debinding? So it's not required actually ultrasonic. What you need is a bath where you can put acetone and ideally where you can heat. And ultrasonic is just the most simple thing we could find to do that. It is included in the TK package, absolutely. About the firing cycle for ceramics or for 316L, well, actually, it can be for both, but it really depends on the part. If you have a very thick part, it may be longer. The firing, what takes time in the firing is not actually sintering, it's the thermal debinding. Yeah, both can be done in 24 to 48. It really depends on the thickness of the part. So does the alumina finished product considered aluminum oxide? I confirm that this is alumina and aluminum oxide. It is the same thing. So yes, once it's sintered, you have aluminum oxide parts. It can go up to 14 degrees Celsius, 1400, a bit more actually even. What it may not like is very high thermal shock. If you go from 14 to room temperature too fast, you may break it. So yes, it can be used as heat insulation, container for molten metals. All of this is possible. Again, you're going to look at, is there too much thermal shock? That might be a problem. But apart from that, yes, absolutely. And when you talk about heat insulation, what's interesting is that you could use what additive brings, which is to make hollow structures, to make structures which are quite complex, so that you improve a lot the heat insulation compared to a bulk material. So it would be possible to use a regular FDM in the market. Absolutely. Actually, the printer we show you is regular. It comes from the market. We usually bring a few modifications, but they're really small. It depends on the printer. And the reason why we chose the bad printer from Race 3D is that first, it's quite a good quality printer, and second, it requires very little adaptation. What may you need to modify? As you show, we modify the spool holder. We usually like the filament to have as little strain on it before going into the extruder. So ideally, if it's on top of the extruder with nothing making any friction, that's better. So sometimes we change the setup so that the spool is placed really on top of the extruder. That's the first thing. The second thing is you may need to modify the extruder if it is too aggressive. Some extruders will have very aggressive wheels that will grind the filament. And if you have that problem, you may modify it. Again, there are a few printers that have the right kind of extruders and that can print directly. And the third thing is we usually like to add a flexible plate because it makes it easier to remove the part without damaging it. But again, yes, you could use a regular FDM printer. Actually, if you have questions on that, the most simple is you can ask us. You tell us, well, I have this printer. Can I use it with your filament? And we're going to tell you yes, no, or maybe. Maybe being we've not tested it. So you're free to test it. And if we say yes, that means we've tested it and we had success. Is it possible to keep the printing part sometime before the first debinding with acetone, or the part will change? Well, to be honest, we've never really tried that. I would say it's possible. What we know is that we've also played a bit with making some first finishing operations on the green part, the printed part, a bit of polishing, of manual polishing, a bit of what could you do? Well, mainly manual polishing, of course, removing the supports. So this is things we've done. So that means the part has waited a bit. We've never seen any significant change. So I would say, yes, it's possible. I don't know if it's advisable to keep it for a very long time, but for a few days or even a bit more, I don't think it would pose any problem. Are there any application of these 3D printed materials in the medical field? Well, we hope so. What I can tell you is the materials we are offering, alumina and zirconia, they are compatible with medical applications. We do have some customers using our base materials, not the 3D printing filaments, but the base materials to make prosthesis, hip, knee, wrist prosthesis, any kind of surgical instruments also. A lot of these things are made with 3D printing. For the moment, I do not think we have any customer printing parts for medical applications. I think that this may take a bit of time because even though the material is qualified, you will need also to qualify the printing process. And we know that takes time. And I must say also that I'm not completely sure that this technology is the best suited, at least for the most demanding applications. I'm not sure I would advise to print a hip prosthesis with this technology. There may be some other application in medical field where it's not very critical in terms of mechanical or in terms of precision, but I'm not sure it's really the technology for the most demanding applications in medical. Do you have some SEM pictures of typical achieved microstructures? Can it really be dense enough? So that's a good question. Well, we do have SEM pictures. I'm afraid I'm not sure I have them here with me. I could check. What I can tell you is we're doing a lot of tests at the moment on microstructures, density, and mechanical strength. And mechanical strength is really something our customers are asking about. So we've done a lot of mechanical tests with Zirconia. We found out that with the right printing parameters, we achieve densities of 99% easily. And the mechanical strength gets really close, a bit below, but really close to the mechanical strength of the bulk material. Something like 10, 15, 20% below the bulk, but not much more than that. So yes, we get to really dense and strong material. Again, we need to ask what are the right applications. And do we need to be at the same level as the bulk material? But still, we manage to get quite dense materials. That's an interesting one. Have you an idea of the infill geometry effect on the mechanical properties of the parts? Well, to be honest, this is something we have not tested at all. That's a good question, which would need to be tested at some point. What I can tell you for sure is that most of the infill geometries, they will induce a very strong anisotropic behavior. Because if you print, for instance, honeycombs, the geometrical structure is very different in Z and X and Y. So that's something which you need to have in mind. There is one type of infill which is isotropic, and which will give you more isotropic properties, which is the gyroid infill, which is a specific type of infill. This one will give you properties which are a bit more isotropic. But exactly the mechanical strength, I don't know. Something to test on the on the future. To whom to ask if I want to get finished sintered 3D printing Zetamix part? Well, Mark, you can go to us. That's the most simple way for a start. We do have a few customers who offer services, printing services, but for a first part, we usually offer to do it ourselves. And then if you have some more needs, you can we can direct you to the right partner for that. But really, I would advise you to come to us. That's the most simple way. I think you have my email, Mark, so you can send me an email if you have anything specific. Do you have information about the reproducibility of the pieces in the same series? Same density, porosity, dimensions, presence or absence of the same defect? So yes, we start having some information. We're starting to have a few information because we've made, for instance, mechanical tests. And when you do mechanical tests, you don't do one part. You need to do 30 or 40 times the same part to have the right information about mechanical strengths. What we did find out is that we have, in terms of density, we don't see any difference. Once we have really a good printing parameters, it's always the same density. But clearly, so density, porosity, dimensions, all of this is very stable. But clearly, for the mechanical strengths, that's a question, because mechanical strengths in ceramics is something which is very dependent on the size of the critical defects, the biggest defects, to make it simple. And this may vary quite a lot from one printed part to another. We found out that what we call the Weibull modulus, the variation in mechanical strength on a series of printed parts is a little bit higher than with material made by pressing, for instance. So we have a little bit more differences in the mechanical strength, and so probably in the size of the critical defect, even though we don't see it on the density, on the dimensions, and the porosity. Is there a technical datasheet available of Zetamix? So there's a technical datasheet, but you won't have you won't have the chemical composition inside. We also have, of course, a safety data sheet, but the precise composition is something we keep secret. It's been patented. Actually, it's been patented 3 times. We have 3 different patents on our filaments formulations. But we don't communicate on the precise chemical composition of Zetamix. Do we have some Weibull models data? So we have them. I can't share you with you because we're going to publish that hopefully soon. And in the next edition of Open Ceramics, which is dedicated to additive manufacturing, we intend to publish some paper with a lab from INSA Lyon, which is called Mateis, which is quite well known in the ceramic field. So you should have these data in a few months. Thank you for the PowerPoint. Oh, by the way, if you want to receive the PowerPoint, you really need to give us your contact info. So that was the formula you had to fill in. If you haven't done it, it's not too late. If you want to receive the slides, you really need to give us at least your email. Which is the density that you normally achieve? Well, again, for ceramics, we go up to 99. The best we've done is 99.5%. Mechanical properties is compared to traditional, to let's say, pressing, you'll have in X and Y almost the same properties, maybe something like 10 to 20% below. And we do see some anisotropy. That means that the Z is a bit less strong than X and Y. So you again lose something like 10%. Well, that's it for me. If you have any other questions, again, I'm very happy to answer them. I'm switching to YouTube because I know a few people are watching also on YouTube. We had a question here. What would you use zirconia powder for? Well, zirconia is used well for a few applications actually. A lot of medical wear parts, aesthetical applications as well. In general, zirconia is considered to be one of the toughest ceramics. So if you compare it to ceramics, you're going to use it if you are in a, let's say, a scenario where there is a lot of mechanical strain, to make it simple, some shock, some torsion, some bending, whatever. And if you compare it to other materials, it's a lot stiffer, it's a lot harder than steel or plastics or whatever, and it's more resistant to heat. So it's going to be really something which is a bit in between. You can use it for blades, you can use it for wear parts, again, medical parts, jewels. It has quite a wide range of applications. I think that's all the questions I had. Well, there's one last one. No, that's all. Well, thank you, Thierry. Well, thank you very much for attending. If you don't have any more questions, I think we'll stop here for today. I hope you found it interesting. Of course, we are always interested in your input. So if you would like us to discuss another topic for the next webinar, you should really let us know. You can send us an email and tell us, yes, you should cover that topic. If you want to receive the slides, of course, you should leave us your contact info, and we will keep this webinar series running, so you can expect a new webinar in a bit more than 1 month. You should follow up our LinkedIn page so that you get posted about these new events. Thank you again, and I hope to see you soon for the next one. Okay.